Alright, we're also going to look at how to solve question 2 on the electric fields worksheet. So this question is very similar to question 1. It tells you that you have two small positively charged objects, A and B. So if I kind of wanted to draw this out, I have object A and we have its charge, and then some distance away I have, oh, we're told that that's 0.12 millimeters. Away from that I have B, and it's got a charge. Now, we're told that the force felt from A, so it would be away from B, and B away from A. They're going to be the same force. We've seen that before, but the value for the force is equal to 3.6 times 10 to the negative 3 newtons. So just kind of have to keep that in mind for the question. That was given right here. So we've got these forces. It's going to be repulsion, just kind of as a side note, right? We have two positive charges, so they're going to be repelled from each other. That's not in the question, but just good to remember. You're asked, what happens when you change the distance in these ways? So again, we want to first set up that this force is coming from K, QA, QB over D squared. Now in part A, we're told that the distance has changed to 0.24 millimeters. And if I want to see how this new distance compares to the original distance, I'm going to see that it went up by, well, it doubled, right? It's twice as large as the original. So I can say that my new distance is equal to 2 times my original distance. Which again, I'm kind of going a bit more of a mathematical way of showing it, but from reading the question you can see if the distance was originally 12 millimeters and now, or sorry, 0.12 millimeters, and now it's 0.24 millimeters, it's doubled. So I can write my force is equal to K, QA, QB, just the charges at point A and B, divided by 2D squared, which is equal to K, QA, QB over 2 squared is 4, D squared, which is a quarter of K, QA, QB over D squared. And we've already learned from here that's equal to K, QA, QB over D squared. So I can go and put that right in there. 1/4 of 3.6 times 10 to the negative 3 newtons. My force can be calculated now quite easily, and we can find that is 9.0 times 10 to the negative 4 newtons. For part B, same thing, but now we want to see again our new distance over our original is going to be 30, or 0.3, sorry, let's do that, 0.3 millimeters over 0.12 millimeters, and that gives us a rate of 5 over 2. So this means that my new D2 is equal to 5 over 2 D1. I'd run through the exact same stuff. Force is equal to K, QA, QB over 5 over 2 D squared. Expanding this out, we're going to have K, QA, QB over 25 over 4, I just squared my fraction, D squared I want to flip this up into the numerator, I have 4 is equal to 4 over 25 times k qa qb over d squared. Again, we've gotten back to k qa qb over d squared, which we know is just 3.6 times 10 to the negative 3. So my force is going to be 4/25 of 3.6 times 10 to the negative 3 newtons, which gives me an answer of 5.76 times 10 to the negative 4 newtons. And my last part here is part C. So my new distance, again, over my original distance. Well, my new distance is 0.36 millimeters, and my original was 0.12 millimeters. So this is equal to a rate of, or an increase of 3 times. So it's 3 times larger, the distance. So final time, exact same kind of procedure. Alright, 3 squared is 9, 9d squared equals 1/9 of k qa qb over d squared equals 1/9 of 3.6 times 10 to the negative 3 newtons equals our final answer, which is 4.0 times 10 to the negative 4 newtons. And that's how you do question 2. Again, it's based on these proportionalities. The trick here is just figuring out what the actual increase in D is as a multiple of the original, not just, it didn't just increase by 12 millimeters or by 18 millimeters or by 24 millimeters. We actually want to see how many times larger D is than it was originally, and then we can just use that number to go and solve through proportionality compared to the original distance and the original force.